Hello, my name is Tao Li. I'm a PhD student from Harvard University. Today, I'm very happy to share with you our work on information design with unknown prior. This is joint work with Ce Li from Boston University. Let me begin with an example of information design to motivate our work. Suppose we have a professor who is writing a letter of recommendation for one of his graduating students, and the receiver of the letter is a recruiter in a company who decides whether to hire the student or not. The student might be an excellent student or an average student. And this is denoted by a random variable, omega. And this random variable is usually called state of the world in the information design literature. The professor knows the quality of the student, meaning he knows the realization of the random variable. But the recruiter doesn't know the quality of the student. And then based on the quality of the student, the professor decides how to write the letter. Write an excellent letter or an average letter or something else. And this information that is transmitted from the professor to the recruiter is called signal in the literature. The professor's utility is the following. If the student is hard, then regardless of the quality of the student, the professor gets one utility. If the student is not hard, the professor gets zero utility. The recruiter's utility is different. The recruiter only wants to hire excellent students. So if he hires excellent student, he gets 1. If he hires an average student, he gets -1. He can also choose to not hire, which gives him 0 utility. So we can see that the recruiter, if the recruiter is rational, then the recruiter should decide to hire the student if, after receiving the signal, after receiving the letter, his posterior belief that the student is excellent is larger than or equal to 0.5. Then the question is, what is the professor's optimal recommendation strategy? How should the professor write a letter to maximize his expected utility? To answer this question, we need to know one more thing. We need to know the distribution of the quality of the student. Let's say the student is excellent with probability P, and we assume that P is less than a half. So the student is average with probability 1 minus P. This distribution is usually called prior distribution, denoted by mu naught, mu 0 in the literature. And the classical information design theory assumes that this prior distribution is known to both the sender and the receiver. Then under this prior belief, let's consider the performance of different recommendation strategies of the professor. The professor can choose to always write an excellent letter, regardless of the quality of the student. This essentially reveals no information to the recruiter. So the recruiter still believes that the student is average with 1 minus P probability, which is larger than a half. So the recruiter will not hire the student. The professor gets 0 utility. Alternatively, the professor can choose to do honest recommendation, revealing full information. In this case, the recruiter will hire the student when the student is excellent. So the professor gets P utility in expectation. Neither of the previous two strategies is optimal. The optimal strategy is to do partial information revelation. When the student is excellent, say excellent, deterministically. When the student is average, still say epsilon, but with some probability, with probability P over 1 minus P. And with the remaining probability, say that the student is average. Under this strategy, whenever the recruiter sees an excellent letter, the recruiter will believe that the student is excellent or average with equal probability. So the recruiter will hire the student, and the professor can get 2P utility in expectation. This is better than the previous two strategies, and this is the optimal strategy. From this example, we can actually see a critical assumption in the classical information design literature, which is the common prior assumption. The characterization of the optimal recommendation strategy heavily depends on a common prior assumption. And this assumption doesn't hold in many practical scenarios. For example, the recruiter may not know the distribution of the student quality. the receiver doesn't know the state distribution mu0. It's also possible that the sender doesn't know the state distribution. So even if the professor sees the quality of the student, that doesn't mean that the professor knows the distribution of quality of the students in the entire university. But the recruiter, on the other hand, because he sees many applications, so maybe he knows the distribution of student quality in the university. It's also possible that the receiver has a prior belief about the state of the world that is different from the sender's belief, and the sender doesn't know the receiver's belief. There are many other scenarios where the common prior assumption may not hold. So that motivates our work. We study repeated information design problems with an unknown prior. And we study such problems under two specific settings. In the first setting, the information designer, and namely the sender, doesn't know the receiver's subjective prior belief about the state of the world. In the second setting, we consider none of the players know the objective state distribution, and the receiver uses a learning algorithm to choose actions. Our main results are to provide learning algorithms for the information designer to achieve sublinear regret. In the first setting, we achieve logarithmic regret. Logarithmic in terms of the number of rounds of logarithmic in terms of the number of rounds of interaction between the two players. In the second setting, we obtain an algorithm with a regret bound that depends on the regret of the receiver's learning algorithm. Okay, let me then formally define the model for the first setting we consider, which is persuading a receiver with unknown subjective prior. In this model, we still have two players, as we saw in the example, sender and receiver. The sender knows the true state distribution mu0. The receiver, on the other hand, doesn't know the true state distribution, but he believes that the state follows some distribution mu star, and we call this a subjective prior belief. Importantly, the receiver's subjective prior belief is unknown to the sender. This is a repeated interaction. So at each round T, the sender will choose a signaling scheme, which is a randomized mapping from states to signals. So S denotes a finite set of signals, and then delta S denotes the set of probability distributions over signals. And then a state of the world will be realized according to the true state distribution mu0. And then a signal will be drawn according to the signaling scheme and realize the state of the world. The receiver doesn't see the state of the world. Instead, he observes the signal. So then the receiver will do a base update from his prior belief, obtain some posterior belief about the state of the world, and then chooses an action, choosing an optimal action according to his utility function, denoted by V. Then the action chosen by the receiver and the state of the world will jointly determine the sender's utility. So as I said, this is an online learning problem. So the two players interact for T rounds. The sender's goal is to learn the prior belief of the receivers while also optimizing the signaling scheme. So he wants to compute the optimal signaling scheme to maximize his utility. Before talking about how to learn the receiver's prior belief mu star, let me talk about how to compute the optimal signaling scheme if we know the receiver's prior belief mu star. This can be solved by a linear program. So the linear program aims to maximize the sender's expected utility over all the possible direct signaling scheme. A direct signaling scheme means that the signal space is equal to the action space, and then each signal is interpreted as an action recommendation for the receiver. So conditioning on the state, conditioning on any state, I draw some action with some probability and then recommend that action to the receiver. If the receiver follows my recommendation, then this is my expected utility. But I have to make sure that my signaling scheme satisfy a persuasiveness or incentive compatibility constraint in the sense that whenever I recommend action A to the receiver, the expected utility of the receiver by taking action A is at least as large as the receiver's expected utility by taking any other action A prime, so that the receiver is willing to take action A. Note that this constraint is related to the receiver's prior belief. The objective is linear and the constraint is linear, so this problem can be solved efficiently. Then let's go back to the question of how to learn the receiver's prior belief U star where we don't know the receiver's prior belief. There is a straightforward attempt or straightforward approach considered by this approach is empirical estimation, which basically uses the empirical distribution of states as an estimate for the state distribution. This approach is considered by previous work related to information design with unknown prior. Unfortunately, this approach doesn't work when the receiver's belief is different from the true distribution of the states, because although we observe the state, we can observe the states which give us an estimate for the true distribution, but that is different from the receiver's belief. And we need to design a signaling scheme that is tailored to the receiver's belief. Even if the receiver's belief is equal to the true state distribution, this empirical estimation approach still suffers at least square root of t regret. Regret is defined to be the total expected utility of the sender by using the optimal signaling scheme minus the actual total expected utility of the sender. The empirical estimation method suffers this regret due to intrinsic sampling error. One of our contributions is to design a learning algorithm, online learning algorithm for the sender to achieve log T regret. Our algorithm learns the receiver's prior belief from the receiver's actions rather than doing empirical estimation. And we do this using a multi-dimensional binary search. Let me explain what I mean by learning the receiver's prior belief from the receiver's actions using a multi-dimensional binary search. We want to search the receiver's prior belief. Right? This is the set of all possible prior beliefs that the receiver could have. A prior belief is just a distribution of a state. So if we have 3 states, then we have a triangle, and including the interior. So the receiver's prior belief is some point inside this triangle. And we want to search this point by designing signaling scheme pi, sending signal S, and then observing the actions chosen by the receiver. This idea is related to the idea of learning from revealed preference in the economics literature. And let me explain this idea in more detail. Suppose we use a signaling scheme pi and send some signal S. Let's consider what action will be chosen by the receiver. Let's say there are only 2 actions, A1, A2. Because the receiver is Bayesian rational, so the receiver will take action A1 instead of action A2 if the expected utility of the receiver by taking action A1 is larger than the expected utility by taking action A2. And this is computed according to the receiver's prior belief, the signaling scheme, the realized signal, and the receiver's utility function. Notice that this is a linear inequality with respect to the receiver's prior belief. This means that we actually have a hyperplane that separates the entire region of prior beliefs into 2 regions. And if the receiver's prior belief is in one side of the region, for example, the left-hand side of the hyperplane, then the receiver will take action A1 because for all of those prior beliefs, the action A1 is better than action A2 for the receiver. If the receiver's prior belief is on the right-hand side of this hyperplane, then the receiver will take action A2. This means that the receiver's action will tell us the region of his prior belief. So let's say we observe that the receiver takes action A1, then that means his prior belief is on the left-hand side of the hyperplane. Then we can continue this process. So in the next round, we try another signaling scheme, send another signal, and then observe the receiver's action again. So we have a different hyperplane that separates the region into two regions. And then the receiver's action will tell us the region of his prior belief. We can continue this process. Basically, we are doing a binary search in this high-dimensional space. We continue this multi-dimensional binary search until we can identify the receiver's prior belief with high accuracy. Then the next question is, how do we actually implement this multi-dimensional binary search idea? There are some existing algorithms that do multi-dimensional binary search, for example, the ellipsoid method. However, the time complexity of ellipsoid method is quadratic in dimension, which is the number of states in our problem. Moreover, the ellipsoid method is not applicable when the number of actions of the receiver is larger than 2. So one of our contributions is to design a specific multi-dimensional binary search algorithm that works for more than 2 actions and also has a time complexity that is better than the ellipsoid method. The time complexity of our algorithm is roughly linear in the dimension. The idea of our algorithm is to estimate the ratio of the prior probability of every state with respect to the prior probability of a specific state. So let's say we have state 1 here, then for every other state, we estimate the ratio between the prior probability of that state with respect to the prior probability of state 1. Because this ratio is a single number, so we can use a single dimensional binary search to estimate that number. And then eventually we can recover the prior belief mu star of the receiver. I will not talk about the details of this multi-dimensional binary search algorithm. And instead, I will talk about the full online learning algorithm we designed eventually. The full online learning algorithm we designed is a exploitation algorithm. So first, we use our multi-dimensional binary search algorithm to learn the receiver's prior belief mu star from the receiver's actions with accuracy epsilon. So we obtain some estimated prior that is close to the true prior belief in L1 distance and most epsilon. And then we do exploitation. We compute the optimal signaling scheme I had from the estimated prior, and then we robustify the scheme so that it is persuasive on the true prior belief of the receiver. The reason why we need robustification is because the signaling scheme that is computed from the estimated prior may be non-persuasive on the true prior. So we need to perturb the signaling scheme a little bit to make it persuasive. Then we just use the robustified scheme in the rest of time. The regret of the algorithm can be easily analyzed. So the regret is upbounded by the exploration time, which is logarithmic in epsilon, as I just described. And then plus the remaining time times the cost of robustification in each round. And it has been shown in previous work that the cost of robustification is at most epsilon divided by P0 squared times D, where P0 and D are some instant dependent constants. Eventually, we just picked the epsilon appropriately, and that will give us a regret bound that is logarithmic in the time horizon T. Okay, so that is the main results for our first setting. Let me then introduce our second setting. Our second setting is about learning to persuade a learning receiver. In this model, we still have 2 players, sender, receiver. Neither the sender nor the receiver knows the true state distribution mu0. Moreover, we assume that the receiver doesn't know the signaling scheme of the sender. So at each round T, before the sender chooses the signaling scheme, the receiver will choose a strategy, which is a randomized mapping from signals to actions. And the receiver chooses this strategy using a multi-arm banded learning algorithm that learns from history, ignoring the signaling scheme that is used by the sender in the current round. And then the sender will choose a signaling scheme that maps states to signals probabilistically. Then a state of the world is realized according to the true distribution, and then a state will be drawn according to the signaling scheme and the state. Then the receiver's action is sampled according to the receiver's strategy and the signal that is sent by the sender. Eventually, the action of the receiver and the state of the world will determine the utilities of both players. We again have this picture showing T rounds of interaction between the two players. So at each round, the environment samples a state observed by the sender, and then the sender sends a signal to the receiver. The receiver takes some action which decides the utility of both players. And then the two players will adjust their strategy over time according to the feedback they observe after each round. Our results for this setting, we assume that the sender knows an upper bound on the regret of the receiver's learning algorithm, denoted by R regret. We prove that the sender can achieve the following regret, which is the square root of the receiver's regret times T, divided by some instant dependent constants. The online learning algorithm we designed for the sender is still an exploitation algorithm. It first fully reveals the states for several rounds so that we can estimate the true state distribution using the empirical distribution of states. And then we do exploitation. We compute the optimal signaling scheme from the empirical distribution of states and then robustify it so that we can make the signaling scheme work for the true distribution and also make it robust against the learning behavior of the receiver. And the degree of robustification we need depends on the regret of the receiver's learning algorithm. So by doing this, we obtain a sublinear regret algorithm for the sender. Summary. We designed online learning algorithms for two settings of information design with an unknown prior. In the first setting, we have a receiver who has a subjective prior belief that is unknown to the sender. We design a logarithmic regret algorithm for the sender using the idea of learning from revealed preference using a multi-dimensional binary search algorithm. For the second setting, where none of the players know the distribution and the receiver is a learning agent, we design a sublinear regret algorithm whose regret depends on the receiver's regret. For future directions, we think the following three future directions are very interesting. Firstly, can we remove the instant dependent constants in our results? In particular, can we remove the dependency on the minimum prior probability of a state? Second direction is to prove a lower bound for our first setting. Can we prove a logarithmic regret bound? For setting 2, I actually have a paper giving a matching lower bound. So we know that the bound for our second setting is 10. Lastly, we also think a non-IID setting might be interesting to consider. Our current setting is a stationary setting. The state distribution doesn't change over time. So what if the state distribution changes over time? That's an interesting question to consider. Okay, you can you can scan this code to find our paper. You can also find a link to our paper in the video description. And thank you so much.